Dark openings. One of the most baffling and bizarre phenomena in the universe, dark openings remain a subject of extraordinary review and interest among space experts, physicists, and other scientists alike. Described by their monstrous gravitational draw and the total absence of visible light, they address a limit beyond which the established rules of physical science stop applying. First speculated by Albert Einstein in 1916 as a consequence of his general theory of relativity, dark openings were simply speculative until mechanical advancements allowed their indirect identification in the 21st century. The turning point came during the 1960s, when experts in space research, the Cygnus group of stars, accidentally discovered an unusual celestial object, a brilliant blue star that emits high-energy X-rays. This star, circling an unnoticed companion, challenged regular explanations until it was made clear that it was caught in a gravitational hug with a massive, dark object, Cygnus X1. The discovery of Cygnus X1 proved the existence of dark openings and began a new era of investigation into these infinite conundrums. Cygnus X1, discovered about 6,000 light-years from Earth, boasts staggering properties. It is extremely dense and uses a gravitational force so intense that not even light can escape its grasp. This defining feature earned it the moniker dark opening, capturing the essence of these enigmatic objects. Following exploration efforts have uncovered a smattering of dark openings. Estimates for the entire universe imply that the Milky Way galaxy alone may be home to over 100 million dark openings. Despite their elusive nature, which makes precise detection challenging, space experts have identified several candidates within our galaxy, ranging from stellar mass dark openings formed from the remnants of massive stars, to supermassive dark openings residing at the centers of galaxies. The gravitational impact of dark openings extends far beyond their immediate vicinity, influencing the components of cosmic progress and determining the fate of surrounding matter. Objects that venture too close confront a destiny shaped by the dark opening's relentless force. They are drawn unyieldingly toward the event horizon, the final turning point, where they are subjected to extreme tidal forces and ultimately consumed by the singularity at the dark opening's core. This catastrophic interaction is known as spaghettification. As an object approaches the event horizon, the gravitational gradient across its length becomes stretched to extremity, contorting it into a filamentary structure resembling strands of spaghetti. The forces applied overpower the internal bonds keeping the object intact, resulting in its disintegration into a stream of matter destined to merge with the singularity. Despite the allure of dark openings as invaluable laboratories for testing the limits of physical theory, they remain shrouded in mystery and intrigue. The mission to unravel their secrecy persists, driven by a desire to comprehend the fundamental nature of spacetime and gravity itself. In the vastness of the cosmos, dark openings remain silent sentinels, beckoning humanity to explore the depths of the unknown and expand the limits of human understanding. Despite the considerable distance separating us from the closest dark openings, some approximately 1,500 light-years away, and concerns about their potential impact, in 2019 researchers achieved a monumental breakthrough by capturing the first clear image of a dark opening, M87, located at the center of the M87 galaxy. This remarkable achievement provided crucial insights into the nature of dark openings and their elusive structure. The visual data revealed that they have intricate layers, challenging the traditional perception of them as solitary entities of pure nothingness. Through meticulous analysis and image stitching, scientists identified 3 distinct layers within a dark opening. At the outermost layer lies the event horizon, a crucial boundary marking the point of no return. Once an object crosses this threshold, gravitational forces become impossible to overcome, resulting in its inevitable plunge into the dark depths. Moving inward, the second layer is the photon sphere, a region where light and dark orbit each other. Any photons venturing here are trapped in perpetual bondage, unable to escape the overwhelming gravitational pull. At the center lies the singularity, the third and final layer, where the laws of physics reach their ultimate limits. Matter undergoes unfathomable compression, collapsing to a point of infinite density. It is within this enigmatic singularity that the familiar laws governing the universe cease to apply, plunging researchers into a realm of profound uncertainty and theoretical speculation. The complexity and variability of dark openings present significant challenges to our understanding. Even though they follow a common 3-layer structure, each dark opening exhibits unique characteristics and behaviors that defy logical categorization. Traditional scientific inquiry proves insufficient, necessitating innovative methods to unravel their mysteries. Indirect observation remains the primary means of study, as direct investigation is impossible due to the immense gravitational forces. Attempts to launch probes into dark openings would inevitably end in destruction, crushed into invisibility by their relentless force. Nevertheless, researchers continue striving to decipher the secrets of these cosmic giants. Numerous theories, ranging from stellar collapse to cosmic dynamics, offer tantalizing glimpses into their behavior and origins. Notably, NASA's study of the cosmic center of M87 revealed compelling evidence of a supermassive dark opening exerting gravitational influence over vast cosmic scales. Despite the mysteries, the pursuit of knowledge persists, driven by humanity's inherent curiosity and thirst for understanding. While dark openings may remain unsolvable, the unwavering commitment of scientific inquiry promises to illuminate the darkest corners of the universe, revealing secrets hidden within. Roy Kerr's groundbreaking work in 1963 provided a model that shifted our perspective on dark openings. He proposed a revolutionary theory of black holes that never stop spinning. Central to Kerr's model was the concept of the ergosphere, an area above and below the dark opening where divergent forces balance gravitational collapse, preventing matter from collapsing further inward. This novel domain displayed curious deviations from conventional physics, suggesting the profound mysteries concealed within dark openings. Perhaps the most captivating implication of Kerr's theory was the prediction of an Einstein-Rosen bridge, informally known as a wormhole. This hypothetical structure represents a potential gateway through spacetime, offering a conduit between distant regions of the universe, or even parallel universes. The idea of wormholes stems from the complex interactions described by Einstein's theory of general relativity. In this framework, existence is woven into a four-dimensional fabric known as spacetime. Massive objects warp this fabric, creating gravitational fields that influence the motion of surrounding matter. Wormholes could theoretically serve as shortcuts through this cosmic fabric, connecting distant points in spacetime and potentially enabling rapid traversal across vast cosmic distances. However, the stability and practicality of wormholes remain subjects of intense speculation and discussion among. At the forefront of this endeavor stands the renowned theoretical physicist community, striving to bridge the gap between Einstein's general relativity and quantum mechanics. These two foundational theories of modern physics, while each remarkably successful within their own domains, remain fundamentally incompatible when applied to the extreme conditions within dark openings. This challenge has given rise to various candidate theories, such as string theory and loop quantum gravity, each offering distinct mathematical frameworks aimed at unifying the forces of nature. String theory posits that all particles are composed of tiny, vibrating strings, and that different vibrations correspond to different particles. This theory also suggests the existence of multiple additional dimensions, beyond the familiar three of space and one of time, where gravity and other forces interact in complex ways. Loop quantum gravity, on the other hand, attempts to quantize space itself, proposing that spacetime is made up of tiny loops woven into a fine fabric. In this model, the fabric of space is granular rather than smooth, and this granularity could potentially resolve the infinite density of singularities by introducing a smallest possible unit of volume. Despite their differences, both approaches aim to explain the internal structure of singularities and offer insights into what may lie beyond the event horizon of dark openings. The success of these theories could answer some of the most profound questions in science. What happens inside a black hole? What existed before the Big Bang? Is time travel theoretically possible? Until a full theory of everything is developed, dark openings serve as cosmic laboratories where the extremes of gravity, time, and space collide. Their study continues to drive technological innovation and philosophical contemplation alike. From ancient myths to modern simulations, the concept of dark, all-consuming voids has captured the human imagination for centuries. Today, as we stand at the edge of discovery, we are no longer merely dreamers, but explorers, armed with data, curiosity, and the tools of science. The journey is far from over. Future space missions, such as the Event Horizon Telescope expansions, James Webb Space Telescope observations, and gravitational wave detectors like LIGO and Virgo, will further illuminate the behavior of dark openings. These instruments promise to deepen our understanding, capturing the subtle tremors of spacetime caused by colliding black holes and the faintest traces of light around the darkest objects in the universe. In the end, dark openings are not just astronomical phenomena, they are gateways to knowledge, challenging us to rethink reality, time, and existence itself. The universe, vast and mysterious, continues to whisper its secrets. And with each whisper heard, we move closer to unlocking the profound truths hidden in the dark. Physicist Michio Kaku, whose groundbreaking work has propelled the study of superstring theory, has introduced concepts that represent a dramatic departure from conventional ideal models. Superstring theory hypothesizes that fundamental particles are not point-like entities but instead microscopic, vibrating strings. These strings, much like the strings of a musical instrument, resonate at specific frequencies, giving rise to the various particles and forces observed in nature. In this paradigm, the universe becomes akin to a grand symphony, with each particle corresponding to a unique harmonic resonance of these fundamental strings. One of the most striking implications of superstring theory lies in its potential to explain enigmatic phenomena associated with dark openings, wormholes, and other exotic solutions to Einstein's equations of gravity. As strings traverse the fabric of spacetime, their dynamic motion leads to the formation of gravitational singularities and topological anomalies. However, the elegance of superstring theory masks its inherent complexity, as it necessitates the existence of additional dimensions beyond the familiar three spatial dimensions and one temporal dimension. These extra dimensions, hidden from direct observation, pose a significant challenge to human intuition. Nevertheless, applied models, such as the analogy of fish inhabiting a two-dimensional lake, provide a glimpse into the elusive nature of these higher-dimensional realms. The compactification of these extra dimensions, akin to the folding of a rolled-up piece of paper, renders them imperceptible at everyday scales, yet their influence permeates the very fabric of reality. While the precise nature of these hidden dimensions remains elusive, their theoretical presence offers a promising explanation for the complex structures and anomalies observed in the universe. Furthermore, the mathematical underpinnings of superstring theory have sparked a renaissance in mathematical physics, revealing profound connections between dynamic mathematical patterns and physical phenomena. Indeed, the pursuit of a theory of everything has catalyzed the union of disciplines, shedding light on the deep interplay between mathematics and the natural sciences. Despite its theoretical elegance and scientific potential, superstring theory remains an untested framework, awaiting experimental validation. The elusive nature of extra dimensions presents a formidable barrier to experimental verification, relegating superstring theory to the realm of mathematical speculation. Nevertheless, the audacious vision of superstring theory continues to captivate the minds of researchers and enthusiasts alike, enticing humanity to embark on a journey of intellectual discovery and exploration. As we venture deeper into the unknown domains of theoretical physics, guided by the illuminating beacon of superstring theory, we confront the vast mysteries of the universe, poised on the threshold of a new era of understanding and enlightenment. The task of unraveling the secrets of quantum dark openings has long perplexed physicists, representing a monumental challenge to our understanding of the fundamental nature of the universe. Despite numerous efforts by physicists to tackle this riddle, the elusive solution has remained beyond our grasp. This has prompted Edward Witten of the Institute for Advanced Study at Princeton to describe superstring theory as 21st-century physics that accidentally fell into the 20th century. However, recent advancements have injected new hope into the quest for understanding quantum dark openings. Several groups of physicists have independently reported a significant breakthrough, revealing that string theory could offer a comprehensive solution to the problem, albeit within the more constrained context of 2 dimensions rather than the full 10-dimensional framework set forth by conventional superstring theory. While this represents a promising step forward, the quest for a complete resolution remains ongoing, with the complexities of the situation presenting substantial obstacles. The search for a unified theory of everything beckons us to probe the deepest recesses of cosmic existence, where the boundaries between reality and theory blur, and the secrets of the universe await discovery. The study of dark openings carries profound implications for our understanding of the universe, challenging our notions of reality and raising questions about the nature of existence itself. The interplay between dark openings and other astronomical phenomena, such as neutron stars and gamma bursts, reveals the intricate processes at work in the cosmos. The exploration of dark openings and their interaction with surrounding matter continues to reveal a wealth of intriguing phenomena. One of the most fascinating aspects of these cosmic giants is their ability to warp spacetime so intensely that they create gravitational waves, ripples in the fabric of spacetime itself. These waves travel outward from their source, carrying information about the dynamics of the event, such as the collision of 2 black holes or the merging of a stellar mass black hole with a neutron star. Detecting these waves has become a powerful tool for studying the universe, particularly since the first direct observation of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015. This groundbreaking discovery has opened a new window into astrophysics, allowing scientists to observe the most violent and energetic events in the cosmos, such as black hole mergers, with unprecedented clarity. As these observations continue to accumulate, they bring us closer to understanding the true nature of dark openings, their formation and their evolution. One particularly puzzling aspect is the behavior of matter as it falls into a black hole. While current models suggest that matter undergoes an extreme transformation as it approaches the singularity, questions remain about the fate of information contained within that matter. This is known as the information paradox, a problem that has perplexed physicists for decades. According to quantum mechanics, information about a particle's state cannot be lost. Yet black holes seem to erase all information that falls into them, challenging the foundations of quantum theory. Resolving this paradox remains one of the key objectives in modern theoretical physics. Furthermore, the potential connection between dark openings and the broader structure of the universe remains an area of active research. Some theories suggest that supermassive black holes at the centers of galaxies play a critical role in shaping the galaxies themselves, influencing their growth, and even driving the formation of stars and planetary systems. The relationship between these cosmic giants and the dark matter and dark energy that dominate the universe is also under intense scrutiny. Understanding how dark openings interact with these mysterious components of the cosmos could be essential to unlocking many of the universe's greatest secrets. As scientists delve deeper into the realm of dark openings, new technologies and observatories are being developed to probe the cosmos with greater precision. Instruments like the James Webb Space Telescope, JWST, Event Horizon Telescope, EHT, and next-generation gravitational wave detectors promise to unveil phenomena previously beyond our observational reach. With their aid, researchers hope to capture high-resolution images of black hole environments, measure the spin and mass of these celestial objects more accurately, and possibly even detect signs of physics beyond the standard model. Moreover, the study of black holes intersects with the fundamental questions of cosmology, the origin, evolution, and fate of the universe. Some hypotheses suggest that black holes could serve as gateways to other universes, or even function as cosmic seeds from which new universes are born in an eternal cycle of cosmic rebirth. While these ideas remain speculative, they represent the bold thinking that characterizes modern theoretical physics. One particularly provocative theory is that of the holographic principle, which posits that all the information contained within a volume of space can be described by data encoded on the boundary of that space. In this view, our three-dimensional reality may be a projection of information stored on a distant, two-dimensional surface, an idea born, in part, from insights into black hole thermodynamics and string theory. This paradigm-shifting perspective challenges our understanding of space, time, and the nature of existence itself. Meanwhile, quantum gravity, the yet unfinished synthesis of quantum mechanics and general relativity, continues to be a frontier of theoretical exploration. Superstring theory, along with its more refined cousin M theory, remains one of the most promising candidates for achieving this unification. Both frameworks suggest that at the smallest scales, spacetime is not smooth but quantized, consisting of discrete, fundamental units woven together in a vast, vibrating network. However, these theories still face formidable mathematical and philosophical hurdles. The vast landscape of string theory solutions, estimated to number in the order of 10 to the power of 500, poses the daunting question of which version, if any, corresponds to our universe. Additionally, without experimental evidence, critics argue that string theory risks becoming unfalsifiable, trapped in the realm of beautiful but abstract mathematics. Yet for many, the allure of string theory lies precisely in its elegance and scope. It attempts to bridge the infinitesimally small and the unimaginably vast, to explain everything from the behavior of subatomic particles to the curvature of the cosmos. In a way, it is the scientific equivalent of a grand narrative, a modern epic that seeks to illuminate the hidden architecture of reality. In this light, the journey of understanding dark openings and the pursuit of a unified theory are not merely scientific endeavors, but humanistic ones. They reflect our deep curiosity, our relentless desire to comprehend the unknown, and our capacity to imagine beyond the limits of present understanding. The exploration of the universe through the lens of superstring theory and quantum cosmology is, at its core, a reflection of our collective imagination, one that dares to question the nature of time, space, and our place within the grand cosmic order. As our tools grow sharper and our minds more attuned to the subtleties of the universe, we inch ever closer to unveiling its deepest mysteries. Whether through black holes, strings, or dimensions beyond sight, the answers we seek may redefine not only what we know, but who we are.